Thank you, Arvin, for this very kind opportunity to talk about Kálmán and the filter. I will actually give a short little personal anecdote towards the end about why I think this topic is so nice and interesting. Yes, so Kálmán and the filter is the topic of today. And I thought we would start with talk a little bit about Kálmán and who he was and his impact on the field, and then say a little bit about the background. So basically, what was known when his foundational paper was published. And then we will talk quite a lot about the Kálmán filter, what it actually is, and some of its properties and some examples. And there will be some concluding remarks. And I don't know if I can keep an eye on the chat if there's any.
Henrik, I will take care of that. And in case there is something urgent, I can interrupt you.
Excellent. I was going to say that if you find any mistakes on the slides or anything like that, you should, of course, interrupt me so we can correct it immediately. Okay, so this is the outline. So let's talk about Kálmán, and here you see him to the right. He was born in Hungary, in Budapest, in 1930, and he passed away in Florida in 2016. So he moved to the US in 1943 during the World War II. I don't have any more information about how that came about. And he did his master and bachelor at MIT in EE in 53 and 54 respectively. And then he moved to New York, Columbia University, where he got his PhD in 57. His advisor was John Ragazzini, who is also quite famous, I think, known for sample data theory, and he worked on the Z transform. And he had many other well-known PhD students, actually, like Loftesade and Urey and some others. Kálmán himself, he moved around quite a lot. He was at Stanford. He was at the University of Florida. That's actually where in Gainesville, where he passed away. But he also held a position at ETH in Zurich in mathematics. And he had, as I said, he has more positions and guest positions. He has quite a lot of famous students. At least if you're a control engineer, I think you recognize most of these names. We have Yamamoto, Eduardo Sontag, Carbonecker, Tryfon Giorgio, Patrick de Wilde, Antulas, etc. So they're quite an impressive collection of PhD students. And here are some of his awards. The IEEE Medal of Honor in 74, Centennial Medal in 84, the Kyoto Prize in 85, the Bellman Controlled Heritage Award in 97, and then the National Medal of Science in 2009. So that was from Barack Obama, who gave it to him. And then we have, of course, the Swedish counterpart, the Nordic Process Control Award, which he was awarded in 2015. And I will actually return to this event later when he was awarded this prize. So that was a little bit about the biography about Kálmán. So let's say some things about his impact in the field. And there's actually a quite nice book called The Control Theory, 25 Seminal Papers in the time span 32 to 81. It was edited by Tamer Bashar, one of our honorary doctors at KTH. And yeah, so as the title says, basically the panel for this book selected the 25 most influential papers in this time span. And just to name a few papers which you will find in there, you have the paper by Harry Nyquist, The Regeneration Theory, which is the Nyquist theorem, which I'm not sure it's on the curtain, but it should be there. We have Norbert Wiener's The Linear Filter for a Single Time Series, which we'll come back to that today. We have Kalle Ostrom and Björn Wittenmark, the self-tuning regulators, which of course are well known in Sweden for control we have Lennart Jung's analysis of recursive stochastic algorithms for 77. And then Kálmán, he has 3 papers in this book. So 3 out of 25 papers in this book is by him. So it's contributions to the theory of optimal control, a new approach to linear filtering and prediction problems, and mathematical description of linear dynamical systems. So the first one is more or less linear quadratic control theory. The second one is the one we will talk about today, the filter. And the third one is basically where he introduces the Kalman decomposition, controllability, observability, etc. All of these are things that are taught today in the basic control course, more or less, not really, but it's been very influential. I'd say there's nobody who has 3 papers out of these 25. There's one who has 2 papers, and maybe if the people in the control engineers in the audience can guess who is the one who has 2 papers. Does anyone guess?
Is it Jung? Is it 77A and B?
No, it's
because it's actually 2 papers there, right?
Okay. I was actually thinking about. I think there is one other with a 2-part paper actually with the dual control. What's his name? The Russian. Nah, but it was not any of those. There's one person who has 2 separate papers. It's George Sames, who inspired a lot of work in robust control. But anyways, Kálmán has been hugely influential. And in this, there's a little comment about the selection of this paper in this book, and they write here that this is the paper that marked the beginning of a new era in filtering and prediction, and big impact on the control of dynamical systems under uncertainty and using imperfect state measurements. It's interestingly, the paper was originally published in the Journal of Basic Engineering. This is the Association for Mechanical Engineers, which seems like an unusual place for an electrical engineer and a systems engineer to publish. But as we will talk a little bit about, his ideas were initially not that, let's say, initially they were not appreciated or accepted. So he had some issues there, I think. So, but in the end, I think you see he got the recognition he deserved. So it's still a very readable paper, so I recommend it. And it's actually 2 interesting deviations from how we teach Kalman filtering today, and I will also show what that is. So let's then talk a little bit about the problem that is actually considered. And Kálmán is actually, he's quite clear that he called the problem the Wiener problem in the paper. So let's think about what is the Wiener problem. So he talks about that we want to estimate a signal, a stochastic signal, using the history and current value of another observed stochastic process. So it could, for instance, be a noisy measurement process, and we would like to estimate some underlying other property that is correlated with the measurement. And we have a stochastic description of this. And then there are 3 cases that one usually considers. It's the filtering case. So filter is in the name of today's talk. So basically what that means, the K is the time now. So you would like to estimate the current state of the unknown variable, and you're allowed to use the history up until this time. The smoothing case is basically where you are interested in a value in the past. So you have more measurements into the future ahead of the time you're interested in. And then you have the prediction case, of course, where you would like to say something about the future. So those are the 3 cases we are interested in. And Wiener considered those. So let's think about the Wiener problem. So in the discrete time, it's usually called the Wiener-Kolmogorov filtering problem. And this is one way to formulate it. A little bit sloppy, perhaps, but I want to give you the general idea. So you have 2 discrete time signals. So K is the time index, X and Y. You can think of Y as this noisy measurement, and X is the unknown signal we would like to estimate. And we have the cross spectrum phi xy known, and now we observe all the values of y until time k, so all the history. And now we would like to compute the current best estimate we can. So basically, we would like to minimize the variance. So this is the Wiener-Kolmogorov filtering problem, and the solution, I'm just going to show it to you here. In time domain, it requires a solution of a so-called Wiener-Hopf integral equation. Usually, you solve it by means of spectral factorization. So you move into the frequency domain using the Z transform. And the answer is more or less something like this. You get a linear filter G, which in the frequency domain has the Z transform like this. It's the ratio between LC and H, where H is a spectral factorization of the spectral density of the output, and L is obtained by as a stable part. You need to make a stable causal anti-causal separation of a function L. So basically, it's this formula. It's not very perhaps easy to just see why the solution is like this. But of course, this is a well-known result that is, I think, still taught today in signal processing. In the paper by this famous paper by Kálmán, he immediately recognizes the problems with this. So this is more or less the background. So when Kálmán's paper came in 1960, this was basically the way you solve the filtering problem. And now Kalman points out 4 issues with this problem, with this solution. That it's first of all to implement it. It's not immediate. Maybe if the cross spectrum or spectrum is available as rational transfer function, you can still do it, but it's not immediate. And often you need to work on numerical solutions of the Wiener-Hopf integral equation. Also, if the problem is non-stationary, more or less saying that you have a finite time horizon, or if there's some process that varies with time. So for instance, if the noise level varies, intensity varies over time, or if the system varies over time, then it's not so clear. You cannot do the frequency domain approach here. And then he points out that this derivation leading up to this equation, it's not very transparent, and why the assumptions are there. So these are very clearly pointed out immediately in Kálmán's paper. So what does Kálmán then do? So this is, let's now move to his setup. So I think the first nice thing is that he recognizes the importance of what we nowadays call a state space formulation of the problem. So he basically assumes that the stochastic process we would like to estimate can be written in this form here. And it's very standard today, but back then, I think he was probably one of the first to recognize this, and this is he exploited it in all those 3 papers. He used this extensively. So what is unknown here is this vector x. So this is now the unknown so-called state. And you can see here that the models A, B, C, D, and N, that's the model of the stochastic process. It can vary with time. It doesn't present a problem here, really. In the Wiener problem, you needed a stationary, a constant model for the solution to be easily solvable. Here, it's not really a problem if the system varies with time. It's kind of doesn't make anything harder. So X is now the unknown. Y is the measurement. U is some control parameter that we can add to the problem. It's basically it's a deterministic signal. So this more or less is not present any more complications. But of course, if you're a control engineer, it's interesting that you can control the process as well. The noise now comes in here. This is a stochastic process W. It's called a process noise. It's more or less uncertainties that affects the physics, so to say, of the plant. It can be electrical noise that is being injected to the plant, for instance. And V here is measurement noise. It's noise to the measurement process. And then he assumes now that these W and V are white noise stochastic processes that has a certain covariance. So they're uncorrelated over time, independent over time, but they have this covariance and cross covariance. So these matrices Q, R, and S will of course come up in the solution. So that's the setup. And then the problem he poses is the following. Assume now we know the measurements now, starting from time 0 up until time k, and we also know the control because we decide that ourselves. So notice also here that in the Wiener problem, often you start at minus infinity. Here we have a clear start. We start at time 0, so whenever the experiment starts. So again, we have this finite horizon problem, and we have a time varying model, which is sort of doesn't really complicate the solution, as you will see. And now we would like to find the best estimate of x, so a vector variable. And it can again then be in the current time, in the future, or in the past. So it's all these three versions are there. There. And then we assume that we know something about the current time where we start. We assume we know the mean value of the current state, or the time when we begin the experiment, and we know something about the variance. And then I will have some notation for what follows. So by x hat k given k, what I mean by that is the estimate of the state at time k given measurements up until time k. X hat k plus 1 given k means looking one step into the future. So the one step ahead prediction. So given measurements up until time k, I want to look one step ahead in time. So what is now the Kálmán solution? I will just basically give you the algorithm now, and then we will say a little bit about why it became so famous, because the algorithm is it's quite easy to state. So basically what you should do is that you should initialize the filter with the mean of, so you take the mean of your initial guess, you start the filters. This is your best guess of the state at time 0, given that you have received no measurements until now. And the initial uncertainty of that is given by P0. So this is more or less before we've taken any measurement. And then we take the first measurement. So we receive the first Y0. We receive the first measurement, which gives us some information about the real X of 0, of course, but it's corrupted by the noise. So then we do a correction. So more or less what you should do is that you should form a prediction error. You take your measurement and you compare it with your best estimate of the state times the matrix C. And if you have a control, you also need to subtract that. So this is how wrong, on average, you can say you are on your prediction. And then you take your previous estimate that we had from the start and you amplify it with a gain here, often called the Kálmán gain today, with this error. And then you received your X hat given K. So in this case, Z given 0, you get your updated. This is your best estimate. Well, I haven't defined what I mean by best yet, but I will. And of course, the interesting thing is here, how should I choose this K? How much should I amplify this difference? Well, that's given by this formula. So it's a recursive formula, which depends now on the previous. So this is more or less an offline. This is all offline data. It's your previous uncertainty. It's the C, which is the model. And R is the noise in your measurement signal. and pk given k, I will use that in the next step. So basically, this is the update. This is how I update and get my best current update of the state. And after that, I take my prediction step. And now I simplify a little bit the formula. I assume that there's no correlation between the process and the measurement noise. So this S parameter is 0. Then more or less what you do is you take your best current estimate and you propagate it forward in time using the model. So this is more or less your physical model. You just propagate it one step. And this is your estimate of the state in the next time given what I know until now. And then I create my p, k plus 1 given k. So this is also that I just propagate one step in time. I take the uncertainty I have here and propagate it one time. And it, of course, depends on how much process noise I have. And this is it, pretty much. Now I just iterate. So in the next time step, I receive measurement y1. Then I compare it to my previous, the estimate of state 1 given the measurement at 1. I multiply it with a new gain, which depends on the history. But notice now that these are basically offline. K given k and pkk and pk plus 1k, those I can actually run before I get the measurement. So this is quite important in a practical scenario that you can more or less do this offline. So it's more or less only this difference that you need to do when you receive a measurement. Of course, those you don't know ahead of time. So this is more or less the cycle. You run, you predict and you correct. You predict and correct recursively in time like this. And if it wasn't clear before, so pk given k, it's more or less the covariance of the error of this state vector given measurement k, and k given k minus 1 is the error of the prediction error. So this is, of course, larger than this. If you have more information, you will, of course, you will have a better estimate of the state. You can also prove a lot of things. For instance, that the Kálmán filter is an unbiased estimate. So if you take the expectation, you basically get the expectation of the real state. This is what you're interested in. And if you have a stationary problem, more or less, if you let time go to infinity and the models do not vary over time, you will get something called algebraic Riccati equations that is satisfied by these P matrices. And I think the Riccati equation is one other equation on the curtain, so maybe that's a topic for another talk. So I will not further go into that. And of course, in the stationary case, you will actually recover the Wiener filter also. The stationary Wiener filter. So why is now this such a famous result? Well, there are several optimality properties. So this is not only a nice recursive algorithm, it's actually the best thing you can do in several ways. And this is perhaps the most well-known optimality property. So now, until now, I haven't really assumed anything about what type of noise it is. But now let's assume it's Gaussian. So the process noise and the measurement noise is a multivariate Gaussian. Then you can show that the Kálmán filter is the minimum variance estimate. So it's best in that sense. And these covariances that I have are the smallest possible. So basically the filter computes the conditional expectation recursively of the states given the past measurements. It's a recursive way to compute this. So if you like, you can also think of the Kálmán filter as a recursive Bayesian filter for the Gaussian distribution. So it's an efficient way to compute a Bayesian filter. And to connect to previous curtain talk, we had a talk about the Bayes theorem last year, I think. So you see here, this is a way to more or less implement. Under the Gaussian assumption, it's a way to implement the Bayes theorem in an efficient manner. So this is one optimality property. There's another one, and I should say that Kálmán proves both of these in his paper. So he's quite careful about motivating and why this filter is good in a way. So he's very careful. So assume now that the noise is uncorrelated with x0 and white, but it doesn't have to be Gaussian. So now no assumption about the Gaussian. Then the filter is actually the best linear estimator you can do. There's no other linear filter that makes a smaller variance in the error. So if you want to do something linear, this is more or less the best you can do. There's no other way. And again, this is also proven by Kálmán in the paper. So an important point here to make is that in the non-Gaussian case, I mean, then it actually made sense to think about nonlinear filters. So there are other classes of filters. You may have heard of particle filters, moving horizon estimators, etc. I mean, those make sense as long as when the noise is no longer Gaussian. But if the noise is Gaussian, I mean, there's no better thing than a linear estimator, and the linear estimator that is best is the Kalman filter. So then there's no point in really trying anything else. This is basically the best you can do. Yeah, so let's say a few things about his derivation. So he actually uses a quite abstract setup. He's using orthogonal projection in Hilbert space, and I think that was quite unusual at the time. He points out that it doesn't seem to have been used in the engineering literature until his paper in 1960. So of course it was known in probability theory how to do this, but it doesn't seem to have been applied before. So he knew the literature very well. Otherwise, I think if you look today, often people, when want to prove the Kalman filter, they use the Riccati equation and show that there's a relation to a completion of squares. So it's a quite different argument being used today often. But here he's basically using a sort of a geometric argument. And then he basically shows that these two optimality properties, as stated, follows from that. So other differences that how it's taught today. First of all, this is from the paper, and here you can recognize the states. So my presentation of the filter was more or less how it's taught today, but this is how Kálmán writes it. Here is the state equation. So x is the same, phi t plus 1t. This is the A matrix, which you can see explicitly can depend on time. It can vary from time step t to t plus 1, so that's fine. U here is the process noise. But you can recognize that there is no measurement noise in this equation. So today we will always put a measurement noise, not only a process noise. But notice that in the discrete case, it's not such a big deal. You can augment x with an extra state and basically call that state the sensor noise state, which is being excited by the process noise. And so you can add it back in if you have an extra state x here. So that is kind of, it's quite easy to include it. But today you would include it directly in the setup. There is though an interesting, when you want to do this in continuous time models using differential equations, it does make a big difference. And there you actually need to have the sensor noise there explicitly. And this is, I will return to that also a little bit in a while. So that is one difference to how we usually teach it today. Another one is that here is the solution. Here you also see that Kálmán always speaks about this as the Wiener problem. Today we will talk about the Kálmán filter problem, right? No, but he calls it the Wiener problem. So what he's doing here is more or less, he propagates the one step ahead predictor all the time. He doesn't do this predict and correct. To be fair, he does show how you get how you go from here to the next, but he doesn't include it in the algorithm. So this is more or less a tiny difference, perhaps, but often from an application perspective, it's quite important how you choose to implement it. Let's look at a very simple example how this works. This was the simplest example I could think about. So assume we would like to estimate a constant scalar x. So x is 0, say, and it doesn't change with time. So it's, you see, xk plus 1 is x. So the physics is basically the x is unknown, and we don't know that it's 0, but we get a measurement of x with some noise that in this case has variance 1. And let's compare now. For a control engineer, you would typically, to make an estimator, you would often assume some sort of Leuenberger type observer. You would take your current estimate, you would amplify it with some gain minus some gain, multiply with the prediction error here. You compare the measurement with your current best estimate, and the error is being used as an update. And then you can update the value of k here. And of course, the Kalman filter obtains this form, but it gives you the optimal choice of k, which depends then on the measurement noise and the process noise. There's no process noise in this case, and also the initial uncertainty, which I forgot to put here on this slide. Here is just a simulation to show you how this would look like. Here are some different values of k. These are the estimates. So initially we think that the state is 1, and then as we receive new measurements, you see how we update. And the blue one is now when we use the Kalman gain. So that is the optimal, and you see that it's relatively quickly converges to the right one, 0. And you see now the trade-off we're facing. If we use a very large k, you get a very noisy estimate, and that is because you say take k times y minus your estimates. So the measurement noise, if you take a large k, you basically say that I trust my measurement a lot. And then, of course, if there's measurement noise, you get a very noisy estimate. If you take a very small k, what you're saying then is basically that I think I have the measurement is not worth so much. I trust more in my model. And then, of course, you get a very slow convergence. So what the Kalman filter does, it gives you the optimal trade-off between this, how much I know about the physics, the process, and how much information there is in the process. And it's a time-varying gain now. So as time goes by, I should decrease the gain. So initially, I don't know so much. So I learn and adapt quickly. But over time, I gradually decrease. And towards the end, I don't care about the measurements anymore because I basically converged all the time. So this is the optimal gain you can, and this of course follows, it's a very simple calculation using the filter. But even this simple example would not be so easy to do with the Wiener filter because it has this clear initial state like that. Here's another example, an early implementation. And I think this addresses also the issue that the paper was not published in electrical engineering, but in mechanical engineering. This is a paper by Thomas Keilat. He wrote about encounters with an interaction with Rudolf Kalman. He says here that, in fact, Kalman's paper had not attracted much attention. This is in the late 50s or early 60s, sorry, until Stanley Schmidt at NASA recognized that it could be applied to the satellite and rocket tracking problem, just gaining prominence because of Kennedy's challenge to land a man on the moon. So basically, it was an engineer at NASA who recognized early that this filter perfectly fitted into these landing. They were building the Apollo project, the moon lander. And he actually, Schmidt, this engineer who wrote this report, he broke up the equations into 2 steps. So that is actually the correct and the update steps that I showed you. So it turned out to be unimportant if the data did not come in a steady stream. So that was actually this engineer who started writing it in that way. And then he also recognized that if the dynamics were nonlinear, which of course in reality they always are, you can basically apply the filter, you apply it to the linearized equations. So in every time step, you linearize the dynamics given your current best estimate. So these A, B, C matrices are linearized. And so he also invented what is called the extended Kalman filter. So this turned out to be actually an early implementation, and yeah, this was already in the early 60s. So it was. So I think after this was known, I think the result became much more recognized. So the extensions, there are many extensions now. So there's the Kalman-Busey filter, which is the correct continuous time limit. As I said, you need to put in a measurement noise to make it well posed. And this was published in the same year, I think later in 1960. So this is also a very well-known paper. There's the extended Kalman filter, which is basically what is Stanley, this nonlinear case here that was invented by Stanley Schmidt. So we teach it in the nonlinear control course. And of course, today, people are interested in distributed implementations of the Kalman filter. There are things like the uncentered Kalman filter, the discriminative Kalman filter, the adaptive Kalman filter, the hybrid. I mean, there's lots and lots and lots of various ways to try to adapt these equations into to solve whatever problem you have at hand. So what about digitalization? Why is it important to us now in digital futures? Well, first of all, I mean, it's already discrete times in a sense. The time is already discrete, so it's a very well adapted to computer implementation for sure. What do they write in this control theory 25 seminal papers? Well, first of all, they say that it's rightfully regarded as an efficient computational solution of the least squares method. Well, this doesn't sound like much that it's just a least squares problem, but it's a little bit more than that, since there are these optimality properties. But in a sense, it's solving a least squares problem. It says the impact on the field of linear systems, statistics, signal processing, identification, feedback control, and adaptive systems has been enormous. It mentions the moon mission here, but it's also been motivating a lot of new formulations of feasible filtering problems outside the linear domain. So I think it's always a benchmark. Whenever you want to consider a new problem, somehow you always need to compare. I think you're I think motivated or inspired by the Kalman filter and its structure. So, for instance, I think when you want to learn an estimate from data, I mean, we would like to have something recursive efficiently. We would like it to be optimal. This is basically properties that Kálmán has shown that we can do under some circumstances. So this is somehow something we need to relate to. If we want to communicate between two agents in a network, I mean, it's not uncommon that you think about what should I transmit to the other party. Well, if you have a model of the system that you're trying to measure, it's quite common that what you actually transmit, the only thing you need to transmit to the other side of the network is the innovation, namely the prediction error. This is an estimation of what is new in this measurement Y. What is, if the other agent on the other side already had received the previous measurements, what new information is there in this measurement Y? Then you shouldn't transmit the new Y, you should transmit the innovation, what's new in this. And that basically the Kalman filter tells you exactly how to compute this, what to transmit. If you're interested in the trust and security and safety, I mean, it's not uncommon to actually monitor this innovation sequence. The difference between the measurement and this one step ahead prediction like this, you can prove that under Gaussian assumption that this should be a white Gaussian process. So basically you can monitor this signal, and deviations from whiteness or from Gaussianity basically indicates that there is something wrong with the underlying precedence. So in that sense, the Kalman filter also gives you a very convenient way to, in a cheap manner, monitor how the process works. And I'm sure this is just some things I came up with quickly, so I'm sure there's countless other applications you can come up with. So it's a very convenient formula. And now if I'm allowed to have a short personal anecdote, why was I happy to talk about Kálmán filter? Well, it turned out to solve the first problem I worked on when I came to KTH in 2007. I think it's my first paper, I think, with Kalle, who is here, and also with Mikael Skoglund. I don't know if Mikael is here, but I don't know if you remember, but we looked at a problem of a localization problem. So you had a plant, a process that's an agent moving around, and we assumed that there were two sensors available. One that gave rapid measurements of the position of the agent. They were coarse but fast measurements, and then every now and then you received an accurate position, but it was delayed. So, for instance, there was a camera or something in the roof, and it took some time for the camera to process the information, etc. So you basically you had a network, and you would like to, at every time you wanted to compute the optimal position given these streams of data. And of course, after some considerations, we realized that the Kálmán filter solved this problem for us. And so we basically rewrote the problem like this. And you see it's here you can model the measurement of the coarse but fast by choosing a large variance of this measurement. And here you can model the delayed measurements. And there you had a small measurement noise V2 here. And now you see more or less that you have a time varying problem, because it's only for some times k that this C2 is available. So it's a time varying Kálmán filter. So the C matrix is time varying in a varying dimension, but it fits perfectly into the Kálmán's equations, and you can more or less, you can show now that you can find a period that is optimal. So here, for instance, you can see that this estimation error is actually optimal by computing a time-optimal time-periodic filter. So basically, the Kálmán gain here becomes time-periodic in stationarity. So you should basically change the gain periodically like this. And this gives you the optimal estimate at any given time. So it's a periodic switching between these. Anyways, that was the anecdote that's the first, I think the first thing I did at KTH. So anyways, that was pretty much what I wanted to say. I thought there's a lot of recorded material of Kálmán online. I found one clip that I wanted to show you if I'm able to. We'll see if this works or not. So I have a link here. So let's see if I can manage to show this. So can you see Kálmán now?
Yes, we can.
Let's see if you can hear him. I just want to play a little while, but let's see here. And this is actually from this interview when he got the Nordic Process Control Award. It's actually a half an hour long interview. This is just a short. So let's go and see if you can hear.
So now, if you look back again at your career, what would you say is the main decision or event that made it so successful?
Well, there are several factors. One of the things is that, if I may say so, I was an excellent doctoral student in the sense that I did a lot of reading of the literature, I collected a lot of reprints. I spent a lot of time looking around to what was happening and so forth. So as a result of that, the actual genesis of the Kálmán filter was simply a large graduate level exercise consisting of many pieces that had to be put together, but nothing sort of astoundingly different from what was being done. What happened, however, is that probably at that time in the general scheme of things, I was probably the only graduate student who was able to do the exercise because I had the knowledge coming from various sources that allowed me to formulate the problem and to carry through the exercise in solving the problem. This seldom happens, but it does happen.
Yeah, that's good.
So, I don't know if you could hear it, but that was, I think, can you see my slides now?
Yes.
Yeah, so just a few quotes here from him. So he did a lot of reading. So first of all, he said he thought he was an excellent doctoral student. He did a lot of reading of the literature, looking around to what was happening. And then the genesis of the Kálmán field was simply a large graduate level exercise. I think that was his conclusion. And I think by that, I'm actually done. And this is was my take on the Kálmán filter, and of course very happy to answer any questions if there are any. Thank you.